we are going to learn about electron configuration. What is it? How do we figure it out? And why is it important? So you remember the structure of atom, a nucleus at the center made up of protons that are positively charged and neutrons that are negatively charged, and a cloud of electrons surrounding the nucleus. We want to know how those electrons are configured around the nucleus. What is their configuration? Why do we want to know that? Because they are surrounding the nucleus. They are the shape of the atom, outer shape of the atom. So when they come into contact with other species, they are the first things that they come into contact when an atom approaches another atom. So they determine a lot of the properties of the atom, physical and chemical. So they're very important. If we know how they're configured, we can predict a lot of the properties of atom. So you can think of them as pieces of jigsaw puzzle.
I'm the man you call Jigsaw.
That outer shape of each piece of puzzle determines if they're going to fit, if they're going to be a match and fit into each other or not.
So I know a good match when I see a good match.
So a similar situation is the case with electron configuration. Depending on the electron configurations, you would be able to understand if two atoms are able to bond or not. So they're very important in this respect. Just like you have addresses for your houses, the different buildings have addresses. Also, we assign an address for each electron in this system that we're going to learn. So we're going to learn a tool for assigning different numbers to each electron surrounding the nucleus. So just like you have street address, postal code, country, city, name. For electrons, we have quantum numbers. Different quantum numbers give the address of each electrons. For example, and they have different names. Instead of street address, for example, or country, postal code, now you have different names. Principal quantum number, we show that with N. Or you can call it the number of level, just the level of electron, which level the electron is on. And that is basically tells a lot about how much energy that electron has, right? The lower level, the lower energy. The higher level, the higher energy. Next is called sublevel, L, or azimuthal quantum number, also known as orbital angular momentum quantum number.
Excuse me, what?
So you can just call it sublevel. So level and sublevel sometimes are referred to shell and subshell. That's their older version of their names. Nowadays, the most modern name is level, sublevel. Next, we have magnetic quantum number, M sub L. M sub L. And lastly, electron spin quantum number. So we are going to learn what these mean and how the electron configuration around the nucleus look like. Okay. Level number 1, N equals 1. In N, in the first level, you have only one sublevel, and we show that sublevel by number 0. So we're giving the address of the electron. In level 1, sublevel 0. In sublevel 0, the magnetic quantum number is 0. You have only one orbital in sublevel 0. So orbital means the location, if you wish, the electron is probable to exist there. So we cannot exactly pinpoint where the electrons are. We can just talk about the probability of existence within a certain area. So orbital is that area. So level 1 has one sublevel. Sublevel, we call it 0, or we call it S. So we give a letter S also. Same thing. So this is S. 1S, right? Sublevel, level 1, sublevel S, 1S. and has only one orbital, so we show that by a box. Within each orbital, maximally 2 electrons can fit. So spin number, electron spin number, positive half, negative half, that is for 2 electrons. Positive half means the electron is spinning one way. Negative half, it means the electron is spinning the other way. We show those electrons by an arrow up for positive half, an arrow downward for a negative half. And no more than 2 electrons can fit in the orbital. And in fact, 2 electrons with the same electron spin cannot fit in one orbital. They will repel each other. So when they're spinning different directions, they produce a magnetic field opposites each other, so they can attract each other and counterbalance that electric force repulsion, because they both have negative charge. So with the magnetic field that they produce as a result of spinning, they're able to sit together. And we call that the fact that no more than 2 electrons with the same spin can fit in one orbital. We call that exclusion principle. Or a guy named Pauli came up with that, so they called it Pauli's exclusion principle. So based on that, you cannot have more than 1 electron with the same spin in the one orbital. Or you can reframe it in this way. You can say they're not 2 electrons that all 4 of their quantum numbers are the same, right? At least their electron spin number must be different. One is positive half, the other must be negative half, if you're talking about just one single orbital. And that's all there is in level 1. So level 1, 1s, sublevel S, or we call it 0 as well. So 1s has 2 electrons, 1s2, that's how we show it. As a writing, more compact. That's it. That's all there is to level 1. Let's move on to level 2. Level 2 has sublevel 0 as well. So 2s2 is there, just like you saw in level 1. But level 2, you have now a new sublevel as well. Sublevel 1. So level 2 has 2 sublevels. Sublevel 0, S. Sublevel 1 that we show with P. Sublevel P has 3 different magnetic quantum numbers, ML. Negative 1, 0, and positive 1. And in each one of those, we know that we show them with one box. So you have 3 boxes, 3 orbitals. Right? So this one is negative 1, 0, and positive 1, for example. And in each one of those boxes, we said in each one of those orbitals, only maximally 2 electrons with different spin can fit. So the number of level is 2. Now the sublevel is P. P has 3 orbitals. In each orbitals, maximally 2 electrons with different spin can fit. So 2 times 3 orbitals, 6. 2p, 6. So the p orbital can maximally take on 6 electrons. And that's it. That's all there is to the second level. So far you have 1s2, 2s2, 2p6. That's how electrons are sitting, from lowest energy going to the highest. So moving on to the third level. So in the third level, you have sublevel 0, as you've seen before, 3s2. You have sublevel 1, or P. So 0 is S, 1 is P. So that's 3p6. But you also have a new sublevel now, sublevel 2, or we show it as D. So that's sublevel D. Now you have 2 extra orbitals as well. So P had 3, now D has 5 orbitals. The magnetic quantum number is -2, -1, 0, +1, +2. So each one of those belong to one of the orbitals. So 5 boxes, 5 orbitals in total. And in each orbital, as usual, maximally 2 electrons with different spins can fit. So you get 3d. If you have 5 orbitals, in each orbital you have 2. 3d, 2 times 5, that's 10. So that's level 1, level 2, level 3. That's how and it continues. In level 4, again, you have a new sublevel 3, which we show it as F. This is our tool to understand their electron configuration, so we can make some prediction about their properties. So you will see why it's useful later on, or how it's useful. You see, when we go from level 1, 2, 3, 4, it's just natural numbers, increasing 5, 6, 7 to n. The sublevel, since it starts from 0, so when in level 1 you have just 0, in level 2 you have 0 and 1, in level 3 you have 0, 1 and 2, in level 4 you have 0, 1, 2, 3, and in level n you have from 0 all the way to n minus 1. So always the number in sublevels is 1 less than the number of level. ML, the magnetic quantum number, is always for whatever L that you have. For example, for 0 is 0. For sublevel 1 is from -1, 0, and +1. For sublevel 2 is -2, -1, 0, +1, +2. So 5 orbitals, right? This shows how many orbitals you have. So for something that has just, let's say, L, sublevel L, how many magnetic quantum numbers or how many orbitals? So it goes from -L and then it increases to approaches 0. So from -L goes to all the way to 0, and then from 0 goes up to reach +L. So how many orbitals you have in total? Well, from -L to 0, and then from 0 to +L, so that's 2L plus 1. If you have the number of sublevel, for example 0 sublevel, you substitute L as 0, you get 2 times 0 is 0 plus 1, so that's only 1 orbital, just ML equals 0. That's how you can get then how many orbitals you have in a certain sublevel. And then this electron spin is always either positive half or negative half in each orbital, just these two. 2 electrons fit in each orbital with different spins. Let's move on. Here we introduce a visual so that you can see the order by which the electrons sit in those levels and sublevels, fill them up from lowest energy to higher energy. So as we go up here, we have a higher energy. There we go. Let's show you this visual. So first you have sublevel, so level 1, sublevel 0 or S. So I'm going to put an arrow here to show that. So this is the first thing that we fill up. So we call it 1s, and 2 electrons can fit there. So 1s2, 2 electrons so far. Then we go to the next level. We have 2s filling up. So that's 2s, 2 electrons there. And then we come back again, 2p, and then 3s. You see I'm crossing them off. So 2p, how many p? How many electrons on sublevel p? 6 in total. There are 3 orbitals. In each orbital is 2 electrons, so that's 6 in total. And then 3s. We go to the next level, 3s, 2 again. S has 1 orbital, so only 2 electrons on s. Next, we come back again, we do another line, 3p and 4s. So 3p, 6. And next is 4s, 2. Next we have 3d and 4p. And if you have 5, that will be 5s, right? So then I will continue here on the lower line. So next will be 3d, 10. And next will be 4p, 6. And if you have 5, that will be next will be 5s, 2. Before you do again 4d10. So this is now from lowest energy to highest, and we call this a German name, Aufbau.
Achtung, baby! Gesundheit!
Principle. Aufbau principle describes how electrons are filling up from lowest energy to highest energy. Aufbau principle. Aufbau in German means just construction. How those electrons, how electronic configuration is constructed. So as a rule of thumb, you fill them up in the order of increasing n plus L, right? So for example, in here that we first mention 4s2 and then we mention 3d10. Let's calculate n plus n for those. So 4s, n for 4s, n is 4 plus s is 0. L for s is 0. So 4 plus 0, that's 4. For the 3d, however, so n is 3, d is sublevel what? 0 is s, 1 is p, d is 2. So 3 plus 2, that equals 5. So you see, that's why we mentioned 4s before 3d, right? So that's how you want to put them in order, in the order of increasing n plus L. What happens if you have two different situations where n plus the L is equal for them? Then you go by increasing in the order of increasing n. So you first mention the lower n, then you mention the higher n. So n plus L, that's your first rule of thumb for knowing which comes first. And then if you have equal n plus L's, then you go with first the lower n, then the higher n. First the lower level, next the higher level. So that's Aufbau's principle. Now let's see some examples. Alright, let's consider the simplest atom, that is hydrogen, because it just has one proton and one electron. So then that electron sits in level 1, sublevel 0 or S. 1s, how many electrons? Just 1. 1s1. Let's do helium with atomic number 2. That means 2 protons as well as 2 electrons. So they sit in level 1, first, lowest energy 1. Sublevel 0 or S, 1s, how many electrons? 2. So both of them are in sublevel S because S can take up 2, and that's it. We go to lithium, something that is used in batteries nowadays a lot. So 3 electrons, 1s, so S can take maximally 2 electrons, no more. Remember the exclusion principle, Pauli's exclusion principle, no more than 2 electrons, and that has to be with different spins in one orbital. And then from level 1, then we move on to level 2. 1s2, because we still need to have one more electron, 3 electrons in total. So far we have 2. 1s2, 2s, 1. That's it. That's 3 electrons in total. So these superscripts, these are the number of electrons. These coefficients, if you wish, these are the number of levels. And finally, the S, that's like L equals 0, right? Sublevel 0. Okay, let's do another one. Let's do neon, atomic number 10. So that's 1s2. Then we go to the next level, 2s2. I still need more electrons. That's 4 in total so far. So I need 6 more. So after 2s2, Level 2 has two sublevels, sublevel S and sublevel P. So 2p, P has 3 orbitals, so it can take up to 6 electrons. So I need exactly 6 electrons. So 1s2, 2s2, 2p6, that's 10 electrons in total. Let's do now sodium. Sodium, atomic number 11. 1s2, 2s2, 2p6, 3s1, right? Sublevel, the level 2 has only 2 sublevels, so I was done with sublevel 2 after 2p6. Now we go to the next level, level 3, sublevel 0, 3s1. So that's 11 electrons in total. Something interesting, look at neon electron configuration. So you see 1s2, 2s2, 2p6. Now look at sodium, 1s2, 2s2, 2p6, up to here is identical to that of neon, right? So we have another notation for electron configuration. We call it noble gas notation. So instead of doing this for sodium, writing so much, we can do a shortcut and say Na with atomic number 11. I put the neon in squared bracket. The neon is the noble gas right before the sodium on the periodic table. So because noble gases, they have all of their orbitals are complete, you see, S, P, they're all complete. So we use them for a shortcut, and then what is left over, I just write 3s1. So up to neon is the same for sodium, and then the thing that is different is just the 3s1, which gets mentioned there. Let's do another example. For example, potassium, or let's actually do phosphorus. 15. Phosphorus 15. So that's 1s2, 2s2, 2p6, 3s2. So up to 2p6 is like neon. So that's 10. We know already that's 10. That's just like neon. So I need 15. So 3s2, that's 12. 3p3, right? So that's 15 in total. And again, I can just do that as a more concise version, noble gas notation. So I put neon in squared bracket. Doesn't matter if you put its atomic number 10 or not, you can just leave it. So whatever is different, now you mention 3s2, 3p3. So you see, in noble gas notation, the emphasis is on the highest level of electrons. This n equals 3. So the highest n, the last level. And it makes sense because that's more important, because that's the outer shape of the atom. Literally speaking, those jigsaw puzzles, right? That shape is determined by the last level. So that's why we have even a special name for this level. We call it valence level. The electrons that are in that level, we call them valence electrons. Valence is just a Latin word. In today's English, it has changed into value, or in Spanish, valor. Same thing, right? Is the value of that atom, the worth, right? What's the mean, the main meat? What's the most important information is there? The valence level, the electron configuration of the valence level, because that determines the outer exterior shape of the atom and how, when they come into contact with other stuff, if they're going to react or not, if they're a good match or not. So in hydrogen, this is the valence level, 1s1. In neon, the valence level is this, 2s2, 2p6, right? The largest n will give you your valence level. In sodium, the valence level is 3s1. So if I want to do the box diagram for the valence level of phosphorus, for example, so I have 3s2, right? Imagine this box is the s orbital. So 3s2, 2 electrons are in that. Very good. And then you have 3p, slightly higher energy. 3p. P has 3 orbitals. So how do you fill up now those 3 electrons in 3p3? How do you put them? Do you put like 2 here, 2 in the first, and then 1 single here? Or you put the 1 single somewhere else, like in the last one? How do they assume their positions? So we have a rule for that, and it's called Hund's rule. Hund, like Hyundai. Hund's rule. Just the name of a guy who came up with this. Hund's rule says that first the orbitals get half full. So first you put with a spin upward arrows. Once it's half full, then if there's any leftover, you start to fill the orbitals out. That's how it works. Let's see another example. Let's do electron configuration for sulfur. Atomic number 16. So again, up to 16, I know the only noble gas before that is just neon. So I put it, and you can look at the periodic table to tell that, right? So you look at sulfur on the periodic table and you see what is the noble gas before sulfur, and you land on neon. So you put neon into brackets. That's 10 electrons. That would do for you. Now you need 6 more. So neon goes up to 2, remember, 2s2, 2p6. So you just need to go for 3s2, 3p what? So that's 12. You need 3p4. That's it. That's the electron configuration for sulfur. So if I want to show the valence level as a box diagram, so that's 3s2, has 2 electrons in it. It's completely full. And then the slightly higher energy 3p, 4 electrons in 3p, so we have 3 orbitals in p sublevel. How do they land? Again, Hund's rule tells you. So first, make them half full. So all of them upward arrows. 1, 2, 3. Now, I need 1 more electron because we have 4 electrons in total. So 1, 2, 3. Now, you come back, make them half completely full. So that's now 4. This is how they sit. This is how you put them in order. First make them half full, then come back, make them full with a different spin. If you look at the electron configuration of the valence level of sulfur, so N equals 3, right? And if you look at the periodic table, you see sulfur is on the 3rd row. So the highest level that electrons are filling tells you the row on the periodic table. So N equals 3 equals the row on the periodic table. Any element you write down its electron configuration, especially its valence level, the N in the valence level tells you, the highest N tells you the number of row on periodic table. And look at something else. How many electrons in total exist in the valence level of sulfur, right? There's 3s2, 3p4. So 2 electrons on s, 4 electrons on p. So 2 plus 4, that's 6. Look at the column of sulfur. So now depending on the type of periodic table that you have available, some periodic table they say sulfur is on column 16. Some other tables they say it's on column 6a. Some tables they say 6 main. The number of electrons in the valence level tells you, you can tell the column, right? 16 or 6a, that's 6 electrons in the valence level. The 16 is because the 10 columns in between column 1 and 2 and column 3, 4, 5, 6, 7, 8, the 10 transition metals in between. You see the periodic table looks like something like this, right? In between here, there are 10, this part, there are 10 groups. 10 groups, we call them transition metal. And you find a lot of exceptions to what we mentioned today about their electron configuration. There's a lot of exceptions there. So we will focus on those exceptions in another video. But here you know that the highest n in an electron configuration gives you the row on the periodic table, and the sum of all valence electrons tell you the number of column on the periodic table. So let's recap. Just like we have different numbers for home address, we have different numbers for electrons address. We call them quantum numbers. So the first one, the principal quantum number, number of level n, so 1. Then you get to number of sublevel L. We show them also by letters. So the first sublevel letter is S. And then we have magnetic quantum number. Magnetic quantum number, we show that by ML. That determines how many different orbitals exist in a single sublevel. So sublevel S has just one orbital. We show that by 0. So then in each orbital you get the electron spin quantum number. In each orbital you have 2 electrons maximally with different spins. So 1s2. You go to the next level, 2 sublevel S, 2 electrons in sublevel S maximally. Then you have another sublevel in level 2, 2p, now sublevel P, 6 electrons, because P has ml from -1, 0, +1, so that means 3 orbitals. In each orbital 2 electrons, so that gives you 6. Next, that's it for level 2. Level 3, 3s, 2 electrons, 3p, 6 electrons. Level 3 also has sublevel D, but that comes after 4s. 4s, 2, and then you have 3d10. So first comes 4s because that's how they increase in the order of n plus L, increasing n plus L. If 2 of them have the same n plus L, you go by increasing n, Aufbau's principle, lowest energy to highest energy. So you can continue that. So 4p, again 6. And again, before you go to 4d10, you have 5s2, and then 4d10, because if you calculate n plus L, it's lower for 5s and it's higher for 4d. That's why 4d comes next. So now let's count the electrons in each level. In level 1, how many electrons you see in total? Just 2. In level 2, how many electrons in total? So 2s2, 2p6, that's 8. In level 3, how many electrons in total? So 3s2, 3p6, and then 3d10. So that's 2s6, 18. So there is a pattern there. So if you consider level n for a given level, the total number of electrons is given by this formula, 2n squared. That gives you the total number of electrons in a single level. How about for a given sublevel? Imagine you're given the number of sublevel and you're asked how many electrons can fit there. Like sublevel S, we know for S, L is 0. So you can use this formula. So you just need to know how many orbitals in every sublevel exist, and then you multiply that by 2, because maximally 2 electrons can fit in every single orbital. So any sublevel, you can tell the number of orbitals in any given sublevel by this 2L plus 1, right? The magnetic quantum number. And then you just multiply that by 2. That gives you the total number of electrons in any given sublevel. That's all. Hope you guys enjoyed it. Thanks for watching.